Hello, my name is Martin Roden. I want to thank you for purchasing this tape, and I want to particularly thank you for your willingness to invest the time in going through these materials. It is my hope and expectation that the time you spend with this videotape will significantly increase the probability of your passing the PE exam. Something on the order of 40% of the people who take the exam pass, and I certainly want you to be part of that group. You didn't purchase this tape to learn a lot about me, but permit me to say a few things about my background in the hopes that it might increase my credibility and perhaps you'll believe some of the technical things I tell you. I've been teaching at Cal State LA for 31 years. During that time, I authored 15 major textbooks, about 2/3 of those in the area of communications. I've taught courses on instructional television, and I've also taught short courses throughout North America. I authored the chapter on communications in the Great Lakes Press PE Review book. Over the next several hours, I'll be walking you through the solution of a number of problems. Some of them appear in the sample booklet, which is a companion to this videotape. Others are problems that I have added to this basic set. Let me say something obvious. I hope it's obvious at least. This is not the kind of videotape that you should put into your VCR, kick off your shoes, get a glass of wine or a cup of coffee, and sit back and run the tape from beginning to end. You will not get a major benefit from the tape through that kind of passive activity. What I hope you will do is an active learning type of activity. You want to interact with the tape. I would suggest that you look at the introduction to each problem. Stop the tape at that point and try to solve the problem yourself. This is going to tell you which areas you're weak in. Then watch the solution that I go through on the tape, stopping it as often as necessary to look at your reference materials. And then when you finish a problem, go back and try to solve it again without looking at any of your notes. Through this kind of interactive activity, you will gain the maximum benefit from this videotape. And now what we're going to do is a brief introduction that talks about the videotape and also talks about the PE exam. We begin with a table of contents of the tape. The tape is organized into 14 chapters. Some of them are quite short and some of them are rather involved. The first chapter is this introduction that we're talking about now, and we'll talk about the logistics of the examination. Then we'll turn our attention in chapter 2 to the essay problem, problem number 296 in your workbook. We'll follow this with 3 rather simple chapters dealing with problems that are not in your workbook. Then we'll move on in chapter 6 to the first of the multiple choice problems that appears on page 104 of the workbook. We'll follow this with a very simple problem on antenna separation. This problem is not in your workbook. Moving to the second half of the tape, we'll go to the second multiple choice question, problem number 597 in your workbook. Chapter 9 will not solve a problem. It is a very brief tutorial on broadcast AM and FM and on television. We'll follow this with 4 supplementary problems, most of them quite simple, and then conclude with a summary of what we've done on the tape. I want to acknowledge that many of the supplementary problems, the ones that are not in your workbook, are derived from materials that appear in Chapter 7 of Principles and Practice of Electrical Engineering from Great Lakes Press. I wrote Chapter 7, the communications chapter of this book. So now let's talk in general about the examination. It's offered twice yearly, in April and in October. The credentials required to take the exam, the combination of work experience and education, varies from state to state, so you should check your own state's regulations. Although the requirements vary from state to state, the identical exam is administered on a nationwide basis. The topic coverage on the exam includes power systems, that is, generation of power, transmission and distribution of power, utilization, rotating machines, including motors and generators, and lightning, protection, and grounding. The area of electronics contains problems on amplifiers, filters, and operational amplifiers. It includes instrumentation amplifiers and integrated circuits. Problems in the area of instrumentation systems deal with transducers, instrument transformers, and metering systems. In the area of digital systems, you'll find problems covering many of these topics: discrete digital devices and circuits, synchronous and asynchronous machines, digital system implementation, memory and storage devices, microprocessors and computer systems, and computer interfacing protocols and standards. In the area of control systems, you'll find problems in analog and digital controls, feedback control systems, control systems analysis, including stability and gain margin, responsive systems, and industrial and process control. The area of communication systems is what we cover on this videotape. It includes digital and analog systems, broadcast, voice, and data communications, fiber optic systems, antennas, transmission lines, modulation and demodulation, and noise. And finally, the area of biomedical systems contains problems on the electrical applications in living systems. Biomedical instrumentation is on the exam, and also the extremely important issue of safety. Now that we've discussed the topic coverage on the examination, let's talk briefly about the format of the exam and about the scoring. The exam consists of morning and afternoon sessions, 4 hours each, so the entire exam is 8 hours long. There are a total of 24 questions on the exam. 12 of these are essay questions, and they're on the morning exam, and 12 of them are multiple choice questions on the afternoon exam. Regardless of how many of the problems you solve, you need to indicate 4 of the morning problems, the essays, and 4 of the afternoon problems for scoring. Now, the scoring of the essay questions is on a basis of 10 points maximum in 2-point increments. So you can get 0, 2, 4, 6, 8, or 10 points on a problem. Since there are 4 problems you indicate for scoring, the maximum possible score for the morning part of the exam is 40 points. The multiple choice questions each have 10 parts, and each part is worth 1 point. Again, since you will indicate 4 of these multiple choice questions for purpose of grading, the maximum afternoon score is 40 points. Well, what does it take to pass? The maximum possible score, combined morning and afternoon, is 80 points, and you need 48 in order to pass the exam. This represents a 60% pass rate. And it's important to realize this is a combined morning and afternoon score. For example, if you got a perfect score of 40 in the morning, you would only need 8 points in the afternoon to pass the exam. The terminology for the passing score of 48 is minimally competent. Well, you can bring a number of items to the exam with you. Each state sets its own regulations, so you should certainly check the rules for your state. Most state boards allow the use of bound reference material and calculators. Make sure to find out what your state allows. We recommend that you bring one textbook in each of the following areas: power systems and motors, the National Electrical Code, circuits, electronics, controls, digital systems, and communications covering both analog and digital. Other books you may wish to bring with you include mathematical tables, formulas, and conversion factors, review materials, the PE review provided your state permits that, and any other materials that your state might permit. Calculators are very important in taking this exam. You should bring a scientific calculator that does complex number algebra and matrix manipulations. And of course, the best calculator is useless unless you're familiar with the use of it. Bring fresh batteries with you, and if you believe that anything that can go wrong will go wrong, bring at least 2 calculators so you have a backup. Well, let's return again to the scoring of the essay questions for a little more detail. Each question is scored according to a committee-developed scoring plan. One person grades a particular problem for everybody who takes that exam. The scoring plan is devised to determine the competency of an examinee on the questions being asked. And since 60% is the required score to pass the exam, a score of 6 on a particular problem is deemed to be minimally competent on that particular question. Well, we conclude this introductory chapter with a few final comments. If you're solving a problem and the solution is getting overly complex, you're probably doing something wrong. These problems should not get terribly involved. Actually, they've been designed for a subject matter expert, somebody who really knows the material, to solve in about 15 minutes. So you've got about 4 times that amount of time. Again, if it's really getting involved and you seem to need a lot of materials not specified in the problem, you're probably doing something wrong. We'd like to wish you good luck, although certainly luck alone will not pass the exam. We want you to go prepared, and we certainly want you to do well on this exam. Well, now that you know a little bit about the organization of this tape and also about the logistics of the PE exam, we're going to turn our attention to solving problem number 296, which starts on page 54 of your workbook. In this problem, we start with an input to a system. It goes through an attenuator to what is labeled as point A. We then have a lossless coupler, which simply splits the signal at A between points C and B for the purpose of reading the power on a power meter. The fact that the coupler is lossless means that the sum of the powers at C and B is equal to the power at A. The signal at C goes through an amplifier and then on to the output. In solving this problem, we will be moving back and forth from voltage and power levels to their decibel equivalent. Just in case you're not familiar with decibels, let's briefly review them now. The basic definition of the decibel is 10 times the log of a power ratio. Now, if you express this in terms of amplitudes, remember amplitude squared gives you power. So the equivalent of 10 times the power ratio is 10 times the log of the ratio of the squares of the amplitude. And then from the basic property of logarithms, because we have this quantity squared, we can bring the 2 out front and make it 20 times the log of the amplitude ratio. If you want to move backwards from the decibel equivalent to the actual power ratio, all you have to do is raise 10 to the power of the number of decibels divided by 10. Now it's helpful to look at some benchmark power ratios and the equivalent in decibels, and I've put some of them in this table. Notice a power ratio of 1 if the two powers are equal. Since the log of 1 is 0, that represents 0 decibels. A ratio of 2 gives you 3 decibels because the log of 2 is approximately 0.3 multiplied by 10, and that gives you 3 dB. If you multiply by 2 again, you simply add 3 dB. Multiply by 2 again to get 8, add 3 dB to get 9 dB. 10 has a decibel equivalent of 10 dB. This is the only point where the two numbers match. 10 times the log of 10 is 10. Once again, if we double 10 to get 20, we add 3 dB. If we multiply 10 by 10 to get 100, we take 10 plus 10, or 20 decibels. Now let's go back to the problem statement. You're told that the input power to the entire system is 45 milliwatts at a frequency of 63 megahertz. You're told that the attenuator in the system has an attenuation of 11.2 decibels at a frequency between 60 and 70 megahertz. The coupler splits the power to points B and C such that the power at point B, looking up at this diagram, the power at B which goes into the power meter is 6.3 dB below the power at A. And you're also told that this applies in the same frequency range, 60 to 70 megahertz. And finally, you're told that the amplifier has a gain of 15.6 decibels at frequencies between 60 and 70 megahertz. Now let's see what you're asked to do in this problem. You're asked to determine the output power, the power all the way at the right side of the system, in milliwatts. And you're also asked to determine what the power meter reads in milliwatts. What we've done on this slide is simply repeated the system diagram with the various specifications written above the items. So we've discussed this all before. The input is 45 milliwatts at 63 megahertz. The attenuator attenuates 11.2 dB in this frequency range. The coupler splits off power to point B, which is 6.3 dB below the input power. And finally, the amplifier amplifies by 15.6 dB within the given frequency range. Now all we have to do is trace the numbers through the system. You were told that the power at point A is 11.2 dB below the input power of 45 milliwatts. Well, because you were given the attenuation in decibels, we should convert the input power to decibels. We take 10 times the log of 45 milliwatts to get 16.53 dB relative to a milliwatt, dBm. The power at point A is then simply 11.2 dB below this number, or 5.33 dBm. So we're up to point A on the diagram. Well, repeating that, we just found it was 5.33 dBm. The split in the coupler puts a power into the power meter 6.3 dB below this, or minus 0.97 dBm. So we're asked for the reading of the power meter. We already know it in dBm, but let's convert that to the actual power reading. So we have to convert minus 0.97 dBm. We simply take 10 to the power of the decibels divided by 10 to get 0.8 milliwatts. And this is the answer to the second of the two questions in the problem statement. Well, now let's go back. The power at point C at this point is the power at A minus what we just found as the power at B. The power at A was 3.41 milliwatts. The power at B was 0.8 milliwatts. So the power at C is the difference, or 2.61 milliwatts. Notice we're working with power levels and not with decibels. It would not be correct to take the difference of the two dB readings. Now, since we have to put this through the amplifier, which is specified in dB, we need to convert this, the power at point C, into decibels. Well, 2.61 milliwatts equates to 10 times the log of that, or 4.17 dBm. So the power at the output is 4.17 plus the gain of the amplifier, which was specified as 15.6, or 19.77 dBm. Well, we were asked for the power at the output, and we now know it in dB. Let's convert this to the actual power reading. So we take 19.77 dBm, we raise 10 to the power of 19.77 divided by 10 to give us a final answer of 94.8 milliwatts. This concludes problem number 296 in the sample booklet. The previous problem involved a number of numerical calculations. We're now going to take a breather with three very simple added problems. The first of these three problems involves cable loss. Although this problem does not have 10 parts, the way a multiple choice problem on the examination would have, the principles contained within it may well appear on PE examinations. So we're in Chapter 3, and we're doing the first added problem in cable loss. The given situation is as follows. A cable has a loss of 0.41 decibels per 1,000 feet. Now, you may get a problem stated in terms of feet or meters, and you certainly should be able to convert back and forth. You're asked for the total loss for a 10-mile length of this cable, and you're given four choices. We need to convert 10 miles to feet. If the loss had been given per meter, we would convert miles to meters. It's important to note that decibel losses add. Thus, for example, with a loss of 0.41 decibels per 1,000 feet, the loss for 2,000 feet is 0.82 decibels. So the total loss for 10 miles is 52.8 times the loss per 1,000 feet, or 21.6 decibels. The correct answer is therefore selection C. Well, I told you the previous problem would be quite simple. That was somewhat of an understatement. There's a strategy involved here. I've interspersed more complicated problems and simpler problems. I want to raise your confidence, but at the same time not get you cocky about your knowledge of the subject matter. So now we have one more very simple problem, and then I promise you things will get much more complicated. This problem deals with copper conductors. The given problem states that a local copper conductor subscriber loop is 10 miles long. What is the minimum diameter of the copper wire? And you're given four choices. The reason I've put this problem in here is it requires you going to some of your other references to get some key quantities from them. To solve this problem, you need to know a little bit about local loops in telephone systems. A general benchmark that you should be able to find in your references is that the total resistance of a loop should be limited to about 1.3 kiloohms. Doing this will keep the total attenuation below about 6 decibels for a typical output resistance of the electronics. You're also going to need to know the relationship between resistance of a copper conductor and its diameter. If you check the references, you'll find that the resistance is inversely proportional to the square of the diameter, according to the equation given on the slide. In this equation, RDC is the loop resistance in ohms per mile, and D is the conductor diameter in inches. Now that we've located the appropriate formula and the guideline in terms of total resistance, the problem becomes one of simply plugging those numbers in. Since the loop is 10 miles long and the total resistance of the loop is limited to 1.3 kiloohms, the resistance per mile must be less than 130 ohms. So we know RDC has to be less than 130 ohms. So we plug the numbers into the equation and we solve for the diameter. And the diameter is simply 0.029 inches. Therefore, the correct answer to this very simple problem is selection A. Well, now I'm going to make you work a little bit harder. What I've done in this problem, which is not in your workbook, I've taken the system of problem number 296 in the workbook, and I've added some complicating factors to it which borrow from the very simple problems we just solved. We can borrow the system of figure 296 and the characteristics of the copper conductor. The situation we deal with is a band-limited signal with a center frequency of 100 kilohertz. This is transmitted through 2 kilometers of copper wire to a receiver of the type shown in the diagram. Notice this is the same receiver as problem 296. The problem is more complicated than that problem. We're including some attenuation in the characteristics of the channel and also requiring some adjustments for different frequency ranges. Recall in problem number 296, we were very fortunate. All the given specifications were for the same range of frequencies. Continuing with the given information, you're told that the power of the original signal is 505 milliwatts. The attenuator in the receiver has an attenuation of 6 dB at 50 kilohertz. And you're told that this attenuation increases at a rate of 3 dB per octave. So for every doubling of frequency, the attenuation goes up by 3 dB. The lossless coupler splits the input, so the power at point B, that is what goes to the power meter, is 6 dB below that at point A. The output of the receiver must drive a transducer that requires at least 16 dBm to operate properly. So notice in this problem, instead of telling you the gain of the amplifier, we're telling you the required output level. You're asked to find the minimum gain of the amplifier. At first reading, this problem may seem overwhelming. However, if you just approach it one step at a time, you will find it simply combines some of the operations we've talked about previously. We will divide the solution into 3 parts. First, we will find the attenuation in the channel. This will tell us the power at the input to the system. We will then almost be ready to apply the solution technique we used in problem 296. The only additional step is to adjust the receiver attenuator specification, since the frequency is different from that given in the problem specification. Finally, we need to perform the gain calculations just as we did in problem 296. In order to find the attenuation in the copper wire, we need information that is not given in the problem. You should consult your references, and you should be able to find the attenuation of a copper wire in decibels per kilometer as a function of frequency. Note that these represent typical values because the actual values will depend on the diameter of the wire. Once you have this curve, we simply read the value at the frequency of 100 kilohertz. From the given curve, we find an attenuation of approximately 4 dB per kilometer at the given frequency. This means that a distance of 2 kilometers introduces 8 dB of attenuation. Then, since we start with 505 milliwatts, we need simply decrease this by 8 dB. Well, we'll convert 505 milliwatts to decibels to get 27 dBm, and reduce this by 8 to get 19 dBm received power. We can convert this from decibels to a power level to get 80 milliwatts. Another way to do this calculation is to convert the 8 dB of attenuation into a factor of about 6.31. Remember, we take 10 to the power of the number of decibels divided by 10. So we take 10 to the power 0.8 to get 6.31. We can then divide the input power of 505 milliwatts by this 6.31 to get 80 milliwatts. So we're doing the entire problem with power levels rather than decibels. I personally find the decibel approach shown on the slide to be easier. Either way is acceptable, but we're going to need the power level expressed in dB for the next part of this problem. We now need to look at the attenuator in the receiver. You're told that this attenuates the signal by 6 dB at 50 kilohertz. You're also told that the attenuation increases at 3 dB per octave. Thus, at the given frequency of 100 kilohertz, which is 1 octave above 50 kilohertz, we need to increase the attenuation by 3 dB. The attenuation is therefore 9 decibels. So the power into the coupler is the input power minus the attenuation, or 10 dBm. Converting this to a power level yields 10 milliwatts. The amount of power going to point B is 6 dB below that at point A. In other words, the amount of power coming down to the power meter is 6 dB below the power at point A. This means that 1/4 of the power at point A is diverted to the power meter. The meter therefore reads 2.5 milliwatts. The remaining power to the amplifier, that is at point C, will be 7.5 milliwatts. And this translates to 8.75 dBm. The problem specification stated that we must supply 16 dBm to the output. So we simply have to supply enough amplification to get up to this level. The amplifier must therefore have a gain of 7.25 dB. If we convert this decibel reading to a gain, the reading is 5.3. And this is the answer to this problem. We will now solve problem number 596, which appears on page 104 of the workbook. This is a rather involved and complex multiple choice question. In fact, you may wish to consider stopping the tape at this point and take a little bit of a stretch break. You're going to need all of your energy to work your way through this problem. When you first read this problem, you may think that you need to be knowledgeable in local area networks. In reality, this is not as difficult a problem as it seems. You can reason logically and arrive at the correct answer to many of the parts of the problem using a basic knowledge of electrical engineering. A great deal of information is given in the statement of the problem. You're told that a broadband local area network is implemented using 75 ohm cable. The network is a single cable system and allocates to 6 megahertz video channels. This allocation matches that of a standard NTSC television signal. One of the parts of the problem will ask you about noise floor. You may not be able to find this term in your references. Thankfully, the statement of the problem defines this for us as the noise transferred to a matched load from the network. You are then given the minimum noise level or noise floor of each channel. The problem statement tells you this noise floor is minus 57.2 dBmV, dB relative to a millivolt. The entire network consists of 10 cascaded trunk amplifiers with identical output level. The problem states the carrier level at each amplifier output as plus 20 dBmV. Continuing with the situation, the amplifiers are equally distant from each other, and the path between any two of them has a cable loss of 10 dB and a flat loss of 4 dB. Once again, to save you the trouble of checking all of your references for the definition of flat loss, the problem statement defines this as the attenuation due to all the passive components except the cable. This means the total loss between two amplifiers is 10 plus 4, or 14 dB. Finally, you're given the noise figure of each individual amplifier and its minimum rated output level. The noise figure is 8 dB, and the minimum rated output level is 40 dBmV. Even though you can solve most parts of this problem without knowing about broadband local area networks, let us briefly look at the overall concept. Broadband networks have a distinct advantage when it comes to expansion. They can accommodate a variety of users by dedicating a set amount of bandwidth to a particular application. The graphic on the slide shows a segment of the network, including one amplifier placed between two users. The first of the 10 multiple choice questions states 5 properties and asks which one does not apply to broadband systems. Let's go through them one at a time. Property A states that broadband systems are easier to maintain than baseband systems. Well, there's no reason to expect this to be true. The fact that bandwidth segments are assigned to various users dictates that adjustments are necessary. Therefore, when you come to this part of the problem, you should consider this as the likely correct answer. However, we should still look at the other four possibilities to confirm this assumption. Part B states that broadband can support multiple traffic types. Well, indeed, this is a major advantage of broadband systems, so this statement is definitely true. Looking at C, this states that broadband can transmit signals over a greater distance than baseband. Well, this is true because broadband systems can take advantage of using frequencies that transmit further, and additionally, signal-to-noise ratio usually increases as bandwidth increases. Property D states that broadband systems can support higher data rates than baseband. Clearly, the wider range of frequencies permits faster data transmission. So this is true. Finally, statement E is correct for the exact reason given in the statement. Because baseband signals go down to zero frequency, DC levels are important, and grounding is a serious consideration in baseband systems. So the correct answer to this first part is A. Broadband systems are easier to maintain than baseband systems. That statement is not true. The second multiple choice question can be solved without even referring to the system under consideration. You're asked for the maximum bit rate in a 6 MHz channel, where you're given the carrier level and the noise floor. You're given 5 possible answers. Shannon's channel capacity formula, which we will examine in the next slide, says that the maximum bit transmission rate depends on the bandwidth and on the signal-to-noise ratio. Before looking at Shannon's formula, we will need to find the signal-to-noise ratio. Finding this in decibels simply requires taking the difference between the carrier level and the noise level. Since both of these were given in decibels, the difference is easily found to be 77.2 dB. We need to convert this from dB to an actual power ratio, and we do this to find a signal-to-noise ratio of 5.248 times 10 to the 7th. Now let's look at Shannon's formula. The maximum number of bits per second is simply the bandwidth times the log to the base 2 of 1 plus the signal-to-noise ratio. Well, plugging in these two values yields 1.54 times 10 to the 8th bits per second, or 154 megabits per second. The correct answer is therefore selection D. Notice that in calculating the maximum bit transmission rate, we had to find a log to the base 2. Many calculators do not give you log to the base 2, so you may have to do some simple mathematical operations to derive it. So let's walk through these equations. The log to the base 2 of x, let's call that y. Y is what we're trying to find. What this means is that 2 raised to the power y is equal to x. In other words, the definition of a logarithm is the power that the base must be raised to give you this number. So we have the second equation. Now let's assume we take the log to the base 10 of both sides of this equation. So log to the base 10 of 2 to the y has to equal log to the base 10 of x. Remember, we're trying to solve for y. By the basic property of the logarithm, when you raise 2 to the power y, you can bring the y in front as a multiplying factor. So we have y times the log to the base 10 of 2 is log to the base 10 of x. We then simply solve for y. So to find the base 2 of a number x, The logarithm to the base 2 of that number is simply the log to the base 10 of that number divided by the log to the base 10 of 2. So if your calculator can only find log to the base 10, simply do this operation to find log to the base 2. The third multiple choice question asks you for the gain of each amplifier. 5 choices are given. Recall that the statement of the problem indicated that the amplifiers have identical output levels. For this to be true, the gain of each amplifier must exactly match the losses. The total loss between each pair of amplifiers is the sum of the loss in the cable and the loss in all other passive components except the cable. Both of these numbers were given in the specifications. We simply add these two losses together to get 14 dB, so the correct answer is selection D. Question 4 is a general question about equalizers. It does not require any information from the problem statement. So let's look at each of the 5 statements. The statement in Part A says that an equalizer has one fixed setting for all possible cable lengths. Well, this is not correct, since the setting of the equalizer depends on the cable characteristics. In this problem, we're trying to find the selection that is most correct. So let's look at B. It says that an equalizer compensates for the flat loss in the system. Well, this is not correct, since the entire purpose of an equalizer is to cancel the frequency selective characteristics of a channel. We're looking at statement C, that an equalizer provides a frequency response that is the inverse of a cable attenuation, which increases with increasing frequency. Well, this is a true statement of the purpose of an equalizer. We'll summarize this purpose in the next slide. Continuing now to reinforce our thought that C is the correct answer, let's look at D. An equalizer corrects for the variation in an amplifier transfer function. This is not correct, since the equalizer attempts to cancel the frequency selective effects of the channel, not of the amplifier. And finally, statement E says the equalizer is used to equalize signal levels in all the ports of a multitap. Well, this is not describing an equalizer. It's probably closer to the description of some form of automatic gain control. So looking at equalizers, this slide gives a general statement about the purpose of the equalizer. If we assume that the channel has a certain characteristic, transfer function we'll call h of f, then the ideal equalizer has the reciprocal of this as its characteristic. In a typical system, the only frequency-sensitive portion of the channel is the cable. So as we stated previously, the correct answer to this multiple choice question number 4 is part C. Question 5 deals with derating. It describes a situation where a single 6 megahertz channel is divided into 30 200 kilohertz subchannels. You should double check the arithmetic by multiplying 200 by 30 to make sure it equals 6 megahertz. The problem asks for the carrier level of each of those 30 channels. 5 choices are given for this carrier level. The statement of this problem gave the carrier level for the 6 megahertz channel as 20 dBmV. If we now have 30 separate carriers in this one channel, each of them must have 1/30th of the overall power. We therefore have to divide this level by 30. We do this by subtracting the decibel equivalent of 30 to yield 5.23 dBmV. The correct answer to this is therefore selection C. We're at the halfway point of this lengthy problem. I told you it was a long problem and fairly involved. Even though it's multiple choice, you have to do quite a bit of work to answer this. Remember that you must solve 4 of the multiple choice problems in the afternoon session, and you have 4 hours to do this. So nominally, you have 1 hour for each problem. Question 6 asks us to find the noise floor for a channel. You're given that the temperature is 300 degrees Kelvin and that the bandwidth of the channel is 200 kilohertz. 5 choices are given. Well, if you check your references, you'll find the equation for mean square noise level. This is shown on the slide. The mean square noise level depends on Boltzmann's constant, the temperature, which is given as 300 degrees Kelvin, the resistance, which is given in the problem statement as 75 ohms, and the bandwidth, which is given to be 200 kilohertz. Since the 5 multiple choice answers are given in millivolts, we need to convert from mean square value to a minimum noise voltage level. Thus, we are looking for peak value instead of RMS. We do this by taking the square root and dividing by 2. Plugging into the equation yields the value in millivolts, and we convert this to decibels to get 72 dBmV with a minus sign in front of it to indicate that it's less than 1 millivolt. Note that since we're converting a voltage level, the decibel is defined using a factor of 20 instead of 10. Comparing this with the choice of answers, we find that the correct answer is selection B. The 7th question asks you for the system noise figure of 10 identical amplifiers in cascade. The definition of noise figure is the ratio of input signal to noise ratio to output signal to noise ratio. In our network, we assume the gain exactly matches the cable loss. Therefore, the signal part going through the system remains constant. The noise figure is then found by simply adding the noise from amplifiers 2 through 10 to the noise figure for amplifier number 1. The noise figure for each amplifier is 8 dB, and this is equivalent to a factor of 6.3. Since this relates output to input, the amount of noise added by the amplifier is 6.3 minus 1 for a noise factor of 5.3. The total noise for the 10 amplifiers is then 6.3, the noise figure for one amplifier, plus 9 times the added noise per amplifier. The result is 54, which translates to 17.3 dB. The correct answer is therefore selection B. The next question asks for carrier to noise ratio of the system, including all of the cascaded amplifiers. 5 choices are given. The input carrier level at the input to each amplifier is the carrier level at the output of the previous amplifier reduced by the cable loss and by the flat loss. Thus, the carrier level at the input of each amplifier is 6 dBmV. The noise level at the system output is 10 times the noise level for a single amplifier section. The noise level for a single section is the noise floor plus the noise added by the amplifier, This added noise is called a noise figure. Adding these two numbers together yields minus 49.2 dBmV. Now that we have the noise level for a single section, the noise level for the entire system is simply 10 times this. In decibels, we simply add 10 times the log of 10 to obtain minus 39.2 dBmV as the noise level for the system. We now have both the carrier level and the noise level, so we simply take the difference to find the carrier to noise ratio in dB. This is 45.2 dB. So the correct answer is selection C. Question 9 asks for the maximum permitted output level of each individual amplifier. The specific problem statement reads, assuming that the maximum permitted output level is based on a signal to distortion specification and that distortion products are uncorrelated, the maximum permitted output level in dBmV of each of the 10 cascaded amplifiers is most nearly, and you're given 5 selections. Well, since the distortion products are uncorrelated, this means that power addition applies. That is, the power of a sum is the sum of the powers. Then we must reduce the output level of each amplifier by a factor of 10, so that the total distortion equals that of a single amplifier at the rated output. Reducing by a power of 10 means subtracting 10 decibels. So the maximum permitted output level is therefore 30 dBmV. The correct answer to this part is E. Well, we've arrived at the last part of the question. The number of cascaded amplifiers has now doubled from 10 to 20. And the question asks us what to do with the amplifier output levels in order to keep intermodulation distortion constant. Well, if you were able to answer the previous question, number 9, this one should be a breeze for you. If we have twice as many amplifiers and the distortion powers add together, we must simply cut the amplifier power levels in half. This translates to a reduction of 3 decibels. The correct answer is therefore A. That is, lower the output by 3 dB. And that completes this rather lengthy multiple choice question.